Hello, everybody. Um, we have another ISS transit attempt coming up. This will be take 3. Every time we try this, the clouds moved in. We tried initially a solar shortly after last year's epic solar eclipse, which we got, and then a lunar in the UP. It's February, yes, last month. And now there's one closer to where I live at the very beginning of March. So we are going to attempt this again. This photo is not my photo. This is taken from NASA, but there's the photographer's information below. So hopefully we can do it this time. But I need to get into some of the background stuff real quick, how to prep, how we're prepping for this. Okay, well, first of all, it's in a little town called St. Pierre in Indiana. I had to make sure that this was on Central Time because Indiana's one of those states that's a hodgepodge of mixture of time zones, and then you have sometimes they don't change the time and all that stuff. But anyway, so it is. So, and we're still on standard time, so we're good. Moonrise and moonset calculator. I wanted to know this information to see if it was compatible with the transit information, and it is. So I just added that. I used this website. Everything's at top. You should be able to see it. But we're going to do, I needed to get the information for March 2nd and 3rd, even though the transit is technically on the 3rd, but it's like 4 a.m. in the morning, or 4:25 and some change. So I wanted to know moonrise. Obviously, the moon is going to rise the day before. The day before. Sorry about that. So here's basic information on March 2nd. Now here's March 3rd, and the little moon here, crescent moon, that's the actual time. So it's still going to be decently high in the sky, so we should be good. And the spot actually should be pretty clear. I'll get to that in a minute. So then you go to the transitfinder.com, and it's this red one here. So I zoomed in and blew it up, and we actually, if you look at this, the transit duration's 1.5 seconds. That's the best I've seen it thus far near me. And it's the ISS distance during the transit's only going to be about 724 kilometers. That's actually closer than last time we attempted this and didn't get it. And the moon will be just coming out of a full moon, and it'll be a waning gibbous, but it's still going to be pretty full. So, here's just showing you some of the stuff on here. And my azimuth, the reason why I changed it to South 62 West is because my Burton compass is a quadrant compass. It's not a degree compass. But we'll be able to find the moon in the sky anyway if there's no clouds. And I also converted transit time, local time, to universal time here in the lower right-hand corner, UTC, because I'm going to do something with that here in a little bit. Show you why I did that. And then this here is just the location of where it'll be occurring and zooming in on it. That's all this is. So we zoom in and using this information, and there is a scale bar in here. It's hard to see, but using the scale bar, I estimated it's about 75 meters, the center line from this gully. Well, alright, so that's about 246 feet, so I went to Google Earth and I just drew 246 feet, which happens to be part of this driveway, but we're going to be in the actual road. We're not going to be on anyone's property. So that's the actual location, approximate GPS coordinates. Google Earth gives you the 6 decimals, but I only use 5 because that's as accurate as my handheld is. But I'll be able to find this driveway and stuff too, so we should be okay. The yellow dot with the red inner dot is the location. Same thing here, yellow dot, red inner dot. Just zoomed out a little bit. You can see the town of St. Pierre in the upper right. So this is where our we will be setting up for transit. And I went to Google Street View as well, just to see if we have a clear line of sight. And the elevation is about 700 feet above mean sea level. Google Earth's elevation is not it's not gospel. A lot of people think it is. It really isn't. But this is a flat area, so it's probably pretty close. But if you Google's elevation data really breaks down with lots of tight topography, and that's because of how it was gathered through a shuttle mission in 2000. Shuttle that launched a satellite. But anyway, so what I did here is I just approximated the position of the moon in the sky, because it'll be at about 37-degree inclination. That's about the right size. I guesstimated this, so it might be off a little bit from our actual, for where it'll actually be, but I just wanted to see relative if we were going to have a clear line of sight. And I even rotated the moon to its proper rotation from our vantage point as well. So the reason why I needed universal time is because I did go to dial-a-moon, and that's where I got the picture of the moon you just saw in the last slide. And like I've said before, dial-a-moon uses UT hour. It does not use, it uses universal time. It does not use local time. And this UT hour is for, crap. Now, I know for a fact, I caught this while I was doing this, but apparently I didn't change the slide. This UT hour is actually 6 hours later, so it's 10 a.m. And this slide is incorrect. There's not going to be much difference. I thought I changed this. I didn't. My bad. But as you can see, this is from 10. You're going to see as we zoom in. Here's the, when you click on the moon, it zooms in, and you get all the basic information. I've done this before. And we're just going to take the lower right. See here in the information in the lower right, you can see I did use 10 universal time. That's at the top. But for some reason, the last slide, I put in my error, my original error. Sorry about that. And then from the upper left, which is in the lower left here, we have our basic orbital parameters. Like I've said before, the Earth here is to scale to the moon, and the moon is to scale to the Earth size-wise. But the distance between the two is not to scale. The eccentricity of the moon's orbit is also to scale. The green line is just about where we'll be looking towards the moon. The yellow arrow is Earth's rotational direction. The white arrow is the moon's direction in its orbit relative to the North Pole, which is that yellow-blue dot in the middle. And as you can see, we're moving away from perihelion, moving towards aphelion here, or from perigee to apogee here, and it gives you a lot of helpful information here to use. And so this here is just the moon at the date and time we're going to try to get the transit at. And if you want to use this shot, because I am going to do this too, and because I'm going to show you another example of probably going to do it, of latitudinal apparent rotation of the moon. But if you want to use this image for anything, just remember it is the moon from the previous slide you just saw. But anyway, if you want, go ahead, comment, ask me any questions, and I hope you learned something.